Okay, so in this video, we're going to be talking about the wind tunnel calculations. So just as the diagram here, you have your velocity coming into the airfoil. All right. So on the airfoil, we have our pressure probes, as well as the whole entire thing is attached to a load cell setup. Basically, from that load cell setup, we can get our lift and our drag and our pitching moment. We're not going to be really concerned with the pitching moment, but we'll use our lift and drag forces in our calculations here, okay? So we have the velocity coming in. We're able to measure that velocity with a pitot-static tube, which I've diagrammed here. From the pitot-static tube, we're able to get your total and static pressures, okay? Basically, then what you would do is you'd use those static and total pressures in this equation here. So effectively, we have our total pressure is equal to our static plus our dynamic, okay? You could rearrange this equation. You could say your dynamic pressure is your total minus your static, okay? And we're going to say that dynamic pressure is the pressure, that pressure is equal to 1/2 times rho of air times V of air squared, okay? So from there, we could start to rearrange the equation. So the first thing we're going to do is, we'll say that your P sub T minus P sub S is equal to rho of water times G times H sub T minus H sub S. So basically, your pitot-static tube is going to be connected to manometers, and you'll get manometer heights from that, and you just need to multiply the height difference by rho G to get your dynamic pressure. And again, you set that equal to 1/2 rho air times V of air squared. You should remember this velocity equation from the open channel flow experiment where we have static and total pressures. But in this case, it's a little bit different because, the equation is not quite the same. We have the density of water in the manometers, which we did before in the open channel flow, but now we have the density of air for the moving fluid. So before we had water for the moving fluid and water in the manometer, so the densities were able to cancel out. Either way, when you rearrange the equation, you could isolate V air squared on one side. So V air squared equals rho water times G times H sub T minus H sub S, all over 1/2 times rho air. Okay, so next what you do is you'd simply take the square root of each side, and you could rearrange a little bit. So V air equals square root 2 times rho water times G times H sub T minus H sub S over rho air. Okay, so now what you could do is you could plug the velocity into your coefficient of lift and your coefficient of drag equations. Okay, so coefficient of lift and coefficient of drag depend on your force of lift and force of drag. Again, your force of lift is due to sort of the reaction to the acceleration that you are imposing on the air as the air goes over the airfoil. So as the air goes into the airfoil, let's say it's horizontal, okay? As the air exits the airfoil, basically the top and bottom surfaces, will redirect the airflow such that it's traveling with instead of simply a horizontal component, there's a horizontal and a vertical component, okay? And when you change the direction of something, even if you're not necessarily changing the velocity, the speed of an air particle, you're still accelerating the air upward, okay, or downward, depending on which direction your airfoil is facing. But effectively, the directing, like let's say in a wing, the directing of the air downward will create a positive upward force on the wing and therefore the aircraft, okay? So that's where your force of lift comes from. Your drag force comes from, your stagnation forces on the leading edge, as well as your shearing forces that occur as it goes along the body. Basically, your coefficient of lift, what you're doing is you're creating a dimensionless number, okay? So basically, what these coefficients help with is, scaling and things like that. You can make predictions, based on what, a coefficient is, You can make a prediction if you have the same Reynolds number at a higher speed, then you could relate your coefficients at small scale and large scale as long as you have the same Reynolds number at either scaling. Okay, but what it is effectively is a ratio of your force, whether it be lift or drag, divided by the dynamic pressure by the area. Okay, so again, we talked about the dynamic pressure. We set that equal to 1/2 rho air times V air squared. Okay, and then we're multiplying it by the reference area. Now, the reference area we're going to use is our span, which is the width of the airfoil, and then times the chord length. There could be other softwares and other things that could use slightly different values to calculate the reference area. Other things might be the camber line could be used instead of the chord line. So you could have minor variation, in terms of coefficient of lift between, two things on the same airfoil. But the important thing is that you use the same reference area for both the lift and the drag here. Okay, and that means that they are most comparable. Okay, and that's what you're normally doing with coefficient lift and coefficient drag. You'll be finding the ratio of those two. Basically you want to know how much benefit you'll have in drag versus how much detriment you might have at various angles of attack and things like that. So again, being able to compare these is paramount. So having the same reference area in both equations is important. And we could just do quickly your dimensionless check. Okay, so you have force, which is kilograms dot meters over second squared, and then rho times A times V, you end up having kilograms per meters cubed times area, which is meters cubed, times V squared, which is meters squared over second squared. So again, what we can do quickly is we can cancel out the second squared, okay, and then we could also cancel out our kilograms. That's good. So canceling out the kilograms. We have meters cubed over meters, meters to the fourth over meters cubed. Okay, so you can eliminate meters cubed, meters squared, and you're just left with meters. And you have meters over meters, so they erase quite nicely. And you have no dimension over no dimension. So yeah, that is basically all for the calculations. For this lab, it's like relatively simple calculations, just a lot of repetition. Okay, thank you.